Assalamualaikum and hi everyone. Today I'm going to give you lecture on the application of cross product. There will be three main subtopic for this chapter, which is 4.3 moment of force vector formulation, 4.4 principle of moment, 4.5 moment of a force about a specified axis. Moment of a force vector formulation. The moment of a force F about the moment axis passing through O and perpendicular to the plane containing O can be expressed using the vector cross product, which is R cross product with F. Here R represents a position vector drawn from O to any point lying on the line of action of F. We can determine the magnitude for the moment of a force by moment of a force about point O is equal to force times with the distance, where force is open brackets times the r sine theta, which is also equal to r times f sine theta, where theta is the angle measured between the tail of r and the tail of f. The direction for the moment of a force can be determined based on the right hand rule. Consider there's a position vector of r intersect with the line of action force F. The intersection will produce a moment at O. By curling the right hand fingers from R toward F, the thumb will be directed upward or perpendicular to the plane containing R and F, and this is in the same direction as moment at O. For principle of transmissibility, consider the force F applied at any point of A. Okay, the moment created by F about point O is moment is equal to position vector of RA times cross product with F. However, it was shown that R can be extended from 0 to any point on the line of action of F. Consequently, F may be applied at point B or C, and the same moment will be equal for position vector of RB cross product with F equal with position vector of RC cross F. If we establish x, y, and z coordinate axis, then the position vector R and force F can be expressed as Cartesian vector. Therefore, we can determine using the determination method, which is R cross F is equal to IJK, and then Rx, Ry, Rz, Fx, Fy, and Fz. If a body is acted upon by a system of forces, which is F1, F2, and F3, the resultant moment of the forces about point O can be determined by the vector addition resulting from the successive application. This resultant can be written symbolically as moment about O is equal to summation of position vector of R cross product with F. Let's try the first example. From the figure, determine the moment produced by force F about point O. To solve this problem, first we need to draw the free body diagram so that it will show that you understand the question. And then now we write the coordinate of the position vector. So at B it will be B is 4I plus 12J, okay, meter. Okay, then at A, okay, at A is 12K, 12K meter. Okay, after you draw the free body diagram, we need to determine the force which is expressed in Cartesian vector. So F is equal to F times with unit vector of AB. So what we need to do now is to get a position vector for RAB, which is equal to 4 minus 0 I plus 12 minus 0 J plus 0 minus 12 K. Okay, so RAB is equal to 4I plus 12J minus 12K meter. Then to determine the unit vector UAB is equal to position vector of RAB divided by the magnitude of RAB, okay, which is equal to 4I plus 12J minus 12K over magnitude of 4 square plus 12 square plus negative 12 square root, then equal to 4I plus 12J minus 12K over 17.44. From the question, we know that the force is equal to 2 kilonewton. So now we use this formula to get the Cartesian vector for the force. So F is equal to 2k times with the unit vector 4 plus 12j minus 12k divided by 17.44. So the final answer will be equal to 0.46 I plus 1.38 J minus 1.38 K kilonewton. Now we can determine the moment of a force about point O. You realize that for the force F, there are two position vector that is intersect with the line of action of F, which is represented as ROB and ROA. If you understand the moment of a force concept, so you will know that ROB cross product with F will have an equal moment with ROA cross product with F. Now we perform the equation for ROA. So now using the determinant for I, so we need to cross I and I horizontal. So you will write 0 minus 1.38 minus and then 12 times 1.38, okay, close bracket, write it as I, and then remember J, you must put it negative, okay, and then open bracket, 0 times with negative 1.38 minus then 12 times with 0.46, okay, then this is for J plus K, okay, K slash horizontal and vertical, so you will get 0 times 1.38 minus 0 times 0.46, okay, which is equal to negative 16.56I plus 5.52 J kilo Newton meter. Now you perform for through ROB, so equal to I J K. For I J K, the position vector of ROB is equal to 4, 12 and 0, then 0.46, 1.38 minus 1.38, this is the force, okay, cross product equal to, okay, for I, remember slash vertical and horizontal, so you will get 12 times with negative 1.38 minus 0 times with 1.38 is for I, and then minus, okay, J, remember there is J, for you will take 4 times negative 1.38 minus 12 sorry, 0 times with 0.46 J, then plus with K slash the vertical and horizontal. So 4 times 1.38 minus 12 times with 0.46. Close the bracket, then put it as K. So is equal to similar answer, negative 16.56 I plus 5.52 G kilonewton meter. For the second example, you can try this example. Three forces act on the road. Determine the resultant moment they create about the flange at O. Then determine the coordinate direction angles of the moment at Z. Okay. So for this question, first what we need to do is to draw the free body diagram. So this is the free body diagram. If you can see that there are two position vector that connected or intersect with the forces. So for position vector of ROA, there are two forces, which is force F1 and force F2. Meanwhile, for the position vector of RB, there are one forces, which is force 3. Okay, with all the information, we need to determine the position vector, which is ROA and ROB. And then now we can calculate the moment, resultant moment about point O. So it is equivalent with position vector of RA cross product with F1, and then plus with RA cross product with force 2 plus with ROB cross product with force 3. Okay, so this is the answer for the moment about point O. Okay, there are three force that intersect with the respected position vector, and then we can calculate the magnitude of the resultant moment. We know that the formula is equal to the square root of the resultant moment that we get in the Cartesian vector form. And then before we able to determine the Cartesian direction angle, we need to convert the moment about point O to the unit vector. So the formula of the unit vector is equal to moment about point O in Cartesian vector form divided with the magnitude. So you will have the final answer as 0.394 I minus 0.512 J plus 0.768 K. And then finally, you can use the cos alpha equal to its respected I, J and K to determine the angle. So cos alpha is equal to the I, which is 0.394. So inverse cosine, you will get the angle, and then use the similar formula to determine for beta and gamma. Now we move on to principle of moment. It is also known as a Varignon theorem. It defined as a moment of a force about a point is equal to the sum of the moments of the forces component about the point. So consider the resultant forces F is equal to F1 plus F2. Therefore, we can determine the moment about point O is equal to position vector of R cross product with the F. And then we can further derive the equation by its component, which is equal to position vector of R cross product with F1 plus position vector of R cross product with F2. Okay, consider this example. The force F acts at the end of the angle bracket. Determine the moment of the force about point O using conventional and Cartesian vector methods. Okay. Therefore, if we choose to use the conventional method, what we need to do is to resolve the resultant forces F in X and Y component, which is you will get 400 sine 30 Newton times with the distance, okay, which is 0.2 meter, and then minus 400 cos 30 degree Newton times with 0.4 meter to get the resultant moment at point O. And the result will be 98.6 Newton meter, and you can also write it in Cartesian vector notation, which is the resultant moment at O is equal to negative 98.6 k Newton meter. Then if you use the Cartesian vector notation, first you need to resolve in R position vector of R and F. Okay? We know the magnitude of F is equal to 400. To use in Cartesian vector notation, we need to write both position vector and forces in Cartesian vector notation. For R, it will be in X and Y direction, which is in notation of 0.4i minus 0.2j. Okay, and then for F, it will be in X and Y component, which is 400 sine 30 degree I minus 400 cos 30 degree J. Okay, and then you can calculate the moment at point O equal to cross product of position vector R cross with forces F, which is already resolved in I and J component. So you write it in a determinant form. And then using the determinant, you will also get the same answer as the conventional method, which is negative 98.6 k Newton meter. You can try this example for your exercise. Now we move on to the moment of a force about a specified axis. Let's say you need to determine the moment specifically on y-axis, where the force is applied at axis of OY. You can determine the moment about y-axis by using scalar product, which is force times with distance equal to moment at y and then the distance is equal to r cos theta. However, what about you need to determine a moment at any axis? So, the moment at any axis will be equal to the force times dA, where dA is perpendicular distance from the axis to the line of action of force. We can determine the magnitude of the moment at any axis by using this particular formula, which is the unit direction vector along axis A dot product with open bracket position vector from any point of the specified axis to any point on the line of action F. Cross product with force, and then we get a determinant form, which is in this form. Once you solve the determinant, you will get this form of equation. Consider this first example. Determine the moment produced by the force F, which tends to rotate the rod about AB axis. First, we need to draw the free body diagram. Once you draw the free body diagram, then you can interpret the formula based on the free body diagram. Consider this formula. UAB is the unit vector of the moment at AB axis, and then dot product with open bracket position vector of AD cross with the force line of action F, which is F is equal to negative 600I plus 200J minus 300K. Position vector of AD substitute with BC and BD. Here, unit vector of AB can be determined by dividing AB with the magnitude of AB. In this case, since we choose RAD, therefore the position vector for RAD will be 0.2 minus 0 J, which is equal to 0.2 J meter. In this case, F is equal to negative 600I plus 200G minus 300K Newton. Therefore, write the formula, you will get this determinant form. Refer 0.894 as I, and then 0.447 as J, and then 0 as K. So you can expand your determinant in this form. Now you are able to write the expanded determinant form, which is 0.894 bracket 0.2 times negative 300 minus 0 times 200 close, and then minus. Remember, J is always negative, which is 0.447 open the bracket 0 times negative 300, then minus 0 times negative 600 close the bracket, and then plus 0 open the bracket 0 times 200 minus 0.2 times negative 600 close the bracket,
and then you will have the final answer, which is negative 53.67 Newton meter. You can also express the moment about specified axis, which is AB, in the Cartesian vector form, which is UAB times with the magnitude of MAB, which is equal to 0.894I plus 0.447J times with negative 63.67, then equal to negative 48I plus 20. You can improve your understanding by trying to solve these two problems in moment about specified axis. Now we move to the next topic, which is moment of a couple. So couple can be defined as two parallel forces that have the same magnitude but opposite direction and are separated by a perpendicular distance d. For scalar formulation, the magnitude of couple moment is equal to force times with the distance, where direction and sense are determined by right-hand rule. And for vector formulation, moment of couple can be expressed by the vector cross product using moment equal to position vector cross with the force. Resultant couple moment is equal to two couples at pi, where the moment resultant is equal to m1 plus m2. For more than two moment resultant is equal to summation of cross product position vector cross product with the force. For this example, consider the moment couple for F1, F2 and for F3 and their distance D1, D2 and D3 respectively. For the solution, consider the counterclockwise couple moment as positive. Then the summation of all the moment is equal to negative F1 times with D1 plus F2 times D2 and minus F3 times D3. F1 times with D1 is a clockwise rotation, so it is a negative moment. For F2, with respect to their distance, which is 0.3, the moment couple will be in counterclockwise, therefore it is a positive rotational moment. And then for F3, the distance is 0.5, therefore the rotational moment is in clockwise direction. So for F1, it is a negative since it's clockwise, and then F2 is counterclockwise, and negative F3 is clockwise. So substitute all the value and you will get negative 95 Newton meter in a clockwise direction. Simplification of a force and couple system. Sometimes it is convenient to reduce a system of forces and couple moment acting on a body to a simpler form by replacing it with an equivalent system consisting of a single resultant force Fr acting at specific point and a resultant couple moment Mr. For this example, replace the force and couple system shown by an equivalent resultant force and couple moment acting at point O. So in this example, we have three forces, which is 3 kilonewton, 5 kilonewton, and 4 kilonewton. What we need to do is first to determine the force summation. So in order to solve the force summation, what we need to do is to resolve all of the forces in x and y axis. So get the summation of all the forces in x axis, okay, and then for summation of all forces for y axis, and then you will have a x and y direction of forces. So you use the theorem Pythagoras in order to get the resultant forces. In order to determine the direction, you can use this formula, which is theta is equal to inverse of tangent, open bracket, resultant forces of y divided by resultant forces of x. Then you will get the angle 49.3 degree. And then the moment summation about O axis, we can using the moment force, which is force times with the distance. Here, moment about 0.0 for 3 kilonewton sine 30 degree is 0.2, which is in counterclockwise. And then for cos 3 kilonewton cos 30 degree, it is 0.1 with respect to O. So for you also apply the similar concept for each of the force. Finally, you will get a negative 2.46 kilonewton meter, which is in a clockwise direction.